In this section, we're going to talk about one of the most common applications of calculus, and that is using calculus to model the motion of a particle or some other object in space. Okay. So we can use these vector valued functions to model the position of an object. So r of t, that's going to be the position of an object at time t. In single variable calculus, we learned that the first derivative of position is velocity, the second derivative is acceleration. That still holds true here. The first derivative of this position function is the velocity function. Velocity at time t. We've already been thinking about space curves this way, even if we haven't been describing them concretely in this way. We have imagined that a vector valued function like this, that it's describing the motion of a particle at, and t is time, right? And so at time t, it tells you where the particle is along the curve. The derivative gives us a vector tangent to the curve. Okay, that's the velocity. Notice it contains two pieces of information. The magnitude of the velocity is telling us how fast we're going. Okay, but velocity isn't just about speed, it's also about direction. In single variable calculus, there's only two possible directions you could go, right? You go in the positive direction or in the negative direction. But once we have more dimensions, there are more directions we can point. And so velocity is a vector. It's pointing the direction of motion. And then the derivative of velocity, or the second derivative of the position function, is the acceleration. How much is the velocity changing at time t? So if at this point, maybe our acceleration looks like this, okay? What would that mean if this was our velocity and this was our acceleration? Okay, we could think about acceleration as kind of in two pieces. Hold on. Need to draw the right way. There we go. Okay. There's a piece that tells us how much things are changing in the direction of v. How much are things changing in this direction? Okay, that is communicating change in speed. In this case, since the acceleration is pointing in this direction, we are getting faster as we're going along at this particular point. Okay, we have positive acceleration. But acceleration communicates all the changes of velocity, not just change in speed, but change in direction. Okay, if this was our acceleration, then we're also bending this velocity to the right. Okay? And then if we want to focus on just the speed, we could take the norm of the velocity vector. The norm of our velocity is the speed at time t. Again, velocity generally is direction and speed. The magnitude communicates the speed. The direction tells us the direction of motion. But if we want just the speed, then we want just the magnitude of the velocity. Let's do a quick example. We have a vector function. That vector function is describing the motion of some particle or object in space. Okay? We want to find the velocity and acceleration vectors of this object when the time is -2. Okay? So simple enough. Our position function is r of t. That's given to us. That's negative 3t, negative t to the fourth, t squared plus 5. To find our velocity, we just take the derivative of that. The derivative is negative 3, negative 4t cubed, 2t. The acceleration function is the derivative of velocity. And the second derivative of position, which in this case would be 0, negative 12t squared, 2. Now, we don't want the velocity and acceleration functions here. That's not what it's asking for. It wants the particular acceleration velocity vectors at t equals 2. Or t equals negative 2, rather. Okay, so let's plug in. At t equals negative 2, just plug negative 2 in for each t. First component is negative 3. Second component, if I plug the t in, I plug negative 2 in, negative 2 cubed is negative 8, times negative 4 is 32. And plug the negative 2 into the last component, 2 times negative 2 is negative 4. This is our velocity at t equals negative 2. It is a vector. All right. I want to do the same thing for acceleration. The acceleration at negative 2 of this object, just plug negative 2 in for each t. First component is 0. Second component, if I plug in negative 2, I get 4 times negative 12, that's negative 48. And the last component's 2. Okay? And we're done. Okay? Let's take a moment and interpret the results, though. All right? At this particular moment in time, you could find the position if you want. I'm not going to do it, but you can do it by plugging in t equals negative 2. But at that exact moment, the object would be moving in this direction. Okay? But its direction of motion would be changing. Now, in the x direction, it actually doesn't change at all, right? The acceleration is 0. So there's no change in our velocity. But for the y coordinate, in the y direction, the acceleration is negative 48. Okay? Right now, the velocity is 32, but that negative 48 means that this would be decreasing and decreasing very quickly. Okay? It's going more negative. It's losing negative 48 units of speed per second in the y direction, or per unit of time in the y direction. Okay? And in the z direction, right now it's pointing negative 4 units in the z direction, but it's also losing its speed in that direction because this is pulling it to be more positive. Okay? So generally, at this exact moment in time, our speed would be decreasing. That doesn't mean that that's going to be true for every moment in time, but at the exact instant when time is negative 2, there's no change in x, but in the y and z directions, the speed is decreasing. Okay? As I mentioned previously, acceleration captures two different kinds of changes in the velocity. So if we have some curve, and this is the tangent vector, the velocity here, then an acceleration like this has two components. Has a component in the direction of the velocity that is related to its change in speed, right? And a component orthogonal to the velocity that relates to its change in direction. we would like to be able to characterize both of these components. All right. So to do this, understand that these components are going in two different directions. The acceleration, it has a component going in the same direction as the velocity. So what we want is we want the component going in that direction, which is tangent to the curve. That communicates the change in velocity, the change in speed. Okay, we call it a sub t because it's going in the direction of the unit tangent vector, tangent to the curve. And then there's this other component that's moving orthogonal to the curve. It would be going in the same direction as the unit normal vector. Okay, so that component of the acceleration we call a sub n, since it's going in the same direction as the unit normal vector. And these, as I said, these two components communicate different things. This communicates the change in speed. And the normal component of acceleration is the change in direction. All right, let's find formulas. Let's find ways to calculate these. All right, we could do that pretty straightforward way using our vector arithmetic. All right, so if we think about the angle between them, this component right here, this component, this would be a sub t. That's the component in the direction of the tangent vector, in the same direction as the velocity. Notice it's just the scalar component of a onto v. We've calculated that several times now. Okay, we want to know how much of our acceleration is in the direction of the velocity. Okay, what's going to be a little bit trickier is this component right here, which is the component of the acceleration orthogonal to the velocity. How much is the direction of the velocity changing? So to do that, this is a sub n. We're going to need a little bit of trigonometry here. Okay. So sine of the angle between my velocity vector and my acceleration vector is equal to opposite, a sub n, over hypotenuse, which is the magnitude of the acceleration vector. Okay, so multiply that magnitude of the acceleration vector over to the other side. And we have the magnitude of the acceleration vector times sine of theta equals the component of acceleration in the direction of the normal vector. The component of acceleration normal to the curve and orthogonal to the velocity. Okay, now the angle between two vectors, that's familiar. We have a way to calculate sine of the angle between two vectors. Specifically, recall that the norm of the cross product of two vectors is equal to the magnitude of those two vectors, so magnitude of v times magnitude of a times sine of the angle between them. Okay, this right here, that's a sub n. That's what we want, right? So let's isolate this so we could find a formula for a sub n, one where we don't actually have to calculate the angle between the vectors. All right, all we need to do is divide by the norm of v. So norm of v cross a divided by norm of v is equal to norm of a sine theta, which we use trigonometry to find that that is equal to the normal component of acceleration. Okay, so that gives us our two formulas. The tangent component of acceleration is equal to the dot product between the acceleration and the velocity divided by the norm of the velocity. The normal component of acceleration is equal to the norm of the cross product of the acceleration and the velocity divided by the norm of the velocity. And so we can quickly and easily find how much, what is the change in speed of the velocity, okay? How much are we changing the speed? And a sub n, the normal component of acceleration, how much are we changing the direction of the velocity? Let's take a look at an example. For this problem, we have some curve with this parameterization. This curve represents the position function for some particle or object, okay? And they want us to find quite a bit. They want us to find the unit tangent vector, the unit normal vector, the normal acceleration, and the tangential acceleration at a particular moment in time, okay? So let's make sure we understand all those pieces and how we're going to find them. So first off, remember the unit tangent vector is the unit vector in the direction of the first derivative, okay? Now in this case, we're thinking about this as a position function. So often, instead of calling this the first derivative, we'll call this the velocity, right? Normal vector is similar, the unit normal vector, but the formula is just a little more complex. This is the unit vector in the direction of, and we're going to take r prime cross r double prime cross r prime, okay? And if we translate this to be interpreted as velocity and acceleration, this becomes, right down here, the velocity crossed with the acceleration, and then you cross it again with the velocity, okay? Now, I wanted to re-emphasize that we want the unit vectors in these directions. So it's not enough just to find the velocity. It's not enough just to find this series of cross products. Once we find that vector, we have to normalize it. We have to turn it into a unit vector. Okay? Next, we need the normal component of acceleration and the tangential component of acceleration. So the tangential component of acceleration, remember, is it's going to be the dot product of the acceleration and the velocity divided by the norm of the velocity. Okay, and the normal component of acceleration is the norm of the cross product of the acceleration and the velocity divided by the norm of the velocity. Okay? Okay, so those are the things we need to find. Notice once we find all these things, we would be able to reconstruct the acceleration from the pieces, because the acceleration vector, remember, is the tangential component multiplied by the tangent vector plus the normal component multiplied by the unit normal vector. Okay, now we're not going to do this, but that's why we're finding all of these things. These are all the constituent parts of the acceleration vector. This is how much the velocity is changing its speed, and this is the direction it's changing in. Okay, this is how much the velocity is changing its direction, and this is the direction it's changing in. All right, so let's get started. We need the acceleration, we need the velocity functions. All right, so let's start by just copying down our position function. R of t equals the vector valued function e to the negative t comma 3t comma e to the t. Our velocity is the first derivative of our position Derivative of e to the negative t is negative e to the negative t. Derivative of 3t is just 3. Derivative of e to the t is e to the t. Okay, and we also need our acceleration, which is the second derivative of position. So one more derivative. Derivative of e to the negative t is negative e to the negative t, but I've already got a negative there, so it swaps back to positive e to the negative t. Derivative of 3 is 0, and derivative of e to the t is e to the t. Okay, and now I'm done taking derivatives. I have all the functions that I need to calculate the things that I need to calculate, right? But note that I don't want to find the unit tangent, unit normal vector, these two components. I don't want to find these, a general formula for the whole curve. I only care about what's happening at t equals 0. So rather than trying to evaluate all these formulas with variable t, it's going to be a little bit easier if I plug in t equals 0 now. And that way I can deal with concrete numbers when I plug into this. Okay? So let's find our velocity function at 0. I get negative 1, 3, 1. And our acceleration function at 0, I get 1, 0, 1. Okay? So those are the two vectors I'm going to use to calculate these vectors, these scalars. Okay? Let's start with the unit tangent vector. I want a unit vector in the direction of the velocity vector, but it needs to be a unit vector. Okay? I've got my velocity vector here. So my unit tangent vector, evaluated at 0, it's just my velocity vector at 0, and I need to normalize it. Okay, my velocity vector at 0 is negative 1, 3, 1. I divide by the norm of the velocity, negative 1 squared plus 3 squared plus 1 squared. And so I get negative 1, 3, 1 divided by, and what do I get? 1 plus 9 plus 1, that's 11, so root 11. So my final answer is negative 1 over root 11, 3 over root 11, 1 over root 11. That's the unit tangent vector to the function at t equals 0. Okay, so one down. Next, let's do the normal, the unit normal vector. This one's going to be a little trickier because we got to take a lot of cross products first. Okay, notice though that we'll want to save this result because the norm of it is going to be the numerator of our normal vector, of our normal component of acceleration. Okay? And notice that it does flip around, but because it's in a norm, the length of this is the same whether it's A cross V or V cross A. So it really doesn't matter there. Okay? But it does matter here. I need V cross A in this formula. Okay, A cross V would be the negative of what I want. Okay, the normal component of acceleration at 0, that would be, well, let's okay, we need V of 0 cross A of 0 cross V of 0. So I'm going to calculate this one first. V of 0 cross A of 0. I, J, K. V of 0. Right here, negative 1, 3, 1. A of 0, 1, 0, 1. So negative 1, 3, 1. 1, 0, 1. I'm going to calculate this pretty quickly. Okay, for I get 3 minus 0. For j, I get negative 1 minus 1, that's negative 2. But since it's j, I get another negative, so positive 2. And k, I get 0 minus 3, so negative 3. Okay? Okay, now I'm going to take this result and cross it with V naught. So V of 0 cross A of 0, which is what I just calculated, and then cross that with V of 0. IJK. V of 0 cross A of 0 is 3, 2, negative 3. V of 0 is negative 1, 3, 1. Okay, and again, let's do this pretty quickly. For the I component, I get 2 minus negative 9. That becomes 11. For the J component, I get 3 minus 3, that's 0. And for the K component, I get 9 minus negative 2, that's positive 11. Okay, we're almost done. This is the vector we want the unit normal vector to point in. But we need it to be a unit vector, so we need to normalize it. Okay, so we just need to take this vector and normalize it. So 11, 0, 11. And I have root 11 squared plus 0 squared plus 11 squared. And rather than actually calculate 11 squared, it's not hard, but I know I'm going to have 2 times 11 squared. Okay? And I know what the square root of 11 squared is. That's easy because the square and the square cancel. And so I get 11, 0, 11. I can pull it 11 out of the root. I still have the 2 in the root. If I fully simplify and multiply this scalar through, the 11s will cancel, and I'll be left with a root 2 in the denominator. And that is my unit normal vector. Okay, so 2 down. I've got my unit tangent vector. I've got my unit normal vector. Now let's find our tangential component of acceleration and our normal component of acceleration. These will both be scalars. Okay. Okay. Tangential component of acceleration first. At t equals 0, we want the acceleration vector at t equals 0 dotted with the velocity vector at t equals 0, and then we'll divide by the norm of the velocity at t equals 0. Okay? So the acceleration vector, let's go way back up here. Acceleration vector is 1, 0, 1. Velocity is negative 1, 3, 1. So 1, 0, 1 dotted with negative 1, 3, 1 divided by the norm of the velocity, so that would be the norm of negative 1, 3, 1. The dot product, I get 1 times negative 1, that's negative 1. 0 times 3, that's 0. And then 1 times 1, that's 1. Okay? And looking at this, we immediately know that the numerator is 0. So I don't even need to calculate the denominator, do I? Once your numerator is 0, your denominator doesn't matter. The fraction is just 0. Okay? Which means the tangential component of acceleration is 0. What that means is that this exact moment of time, the change of the velocity tangent to the curve is 0. It's not changing, which means it's not speeding up or slowing down. It's maintaining constant speed. Okay? All right, one more. We need to find the normal component of acceleration. Okay? Normal component of acceleration. So we need to take the norm of the cross product of A and V and then divide by the norm of V. Now we already have A cross V, or rather V cross A anyway. We found it to be 11, 0, 11. right? Oh, I'm sorry. No, wait. Up 1. 3, 2, negative 3. Okay? So the normal component of acceleration, norm of the velocity cross the acceleration, divided by the norm of the velocity. So this was 3, 2, negative 3. And down here, it was negative 1, 3, 1. Okay, let's evaluate. Numerator, we get 3 squared plus 2 squared plus negative 3 squared. In the denominator, we get square root of negative 1 squared plus 3 squared plus 1 squared. So we get 9 plus 9 is 18 plus 4 is 22 on top. Square root of 22. And on bottom, I get 1, 1, 9. That's what, root 11? And I could actually simplify because 22 is 2 times 11. So the root 11s will cancel, leaving me just root 2. Okay? And that is the final piece I needed. Okay? That tells me how much, the amount by which the acceleration is moving orthogonal to the curve, which tells me how much the velocity is turning. So it's not speeding up at all, but it is turning. It's turning inward towards the unit normal vector. Okay? Now, if we put all this together, and the problem doesn't ask for this, but let's do it anyway. If we put this all back together, we should be able to get the acceleration vector back at that moment. The acceleration vector at time 0 was 1, 0, 1. So let's see if we can get it back by putting the pieces back together. We broke it down, we decomposed it. Now let's check our work by putting it back together. Okay? Our acceleration vector at moment 0 should be our unit tangent, or our tangent component of acceleration at moment 0 times the unit tangent vector, plus the normal component of acceleration times 0 times the unit normal vector. Okay? Tangent component of acceleration was 0 times the unit tangent vector, which was, what was it? Negative 1 over root 11, 3 over root 11, 1 over root 11. Negative 1 over root 11, 3 over root 11, 1 over root 11. Plus the normal component of acceleration, which is root 2, times the unit normal vector at time 0, which was 1 over root 2, 0, 1 over root 2. Now, this is a kind of a special case because we don't have any acceleration that's tangent to the curve. All our acceleration is taking place normal to the curve. It's all focused on turning that velocity vector. So this is 0. Okay? But this works out to be, if I distribute that root 2 and simplify, I get 1, 0, 1. Which does match our original calculation for the acceleration times 0. Our math checks out. We decomposed the acceleration vector times 0 into how much of it is moving tangent to the curve, how much of it is moving normal to the curve.